All right, we're going to get going here on 16.2. We're going to look at vector fields, work, circulation, and flux. So we're going to start with the idea of a vector field. So far into this point, you've pretty much just done scalar fields. Even our vector equations were just vectors that pointed to a specific place in, or a specific point in space. What we have here is something a little different where each specific point in space or in the space we're looking at has an associated vector at that location. This would be more like if you were looking at, like say the flow of water down a river. Each place you'd go to would have a specific direction that the water was flowing and speed, like as it went around rocks and things like that. And you could map out then what the vectors were that were associated with that. And so here you can see a little example I already started drawing on. This is essentially a side cut of an airplane wing. You can see here that each one of these little arrows is representing the speed and direction of the fluid, the air going over it. Up here, you see these arrows are longer as the air is going faster over the top, and then these are shorter down here as it goes slower on the bottom. That's actually what creates lift, because fast-moving fluid creates low pressure and slow-moving fluid creates high pressure, and you get this lift then over the top like that. Next here, you can see, again, this is more like a fluid going in a pipe. As the pipe compresses, if it's you have your incompressible fluid or something there, you can see that these vectors that are here representing the flow at this location is longer than these. It's speeding up as it goes into the narrower part. Here you have something more like what a gravitational field would look like if we represented it by vectors, where they would be vectors that all pointed inward. The closer you got to the actual object itself, like the planet or whatever this is here, the stronger the force would be. So we'd have big vectors here and smaller vectors as you went further away. In fact, this is actually what is going to describe it for us, where this will tell us the magnitude of it, and then of course R would be our location vector, telling us what we where we are looking at that point. So the next thing we have here is just another little a function of vectors here, where we just have the path of a projectile going up in a parabola. At every location along there, there's an associated velocity, and that velocity is a vector. It has a magnitude and a direction. Here we've got a gradient of a scalar field. The gradient of a scalar field will give us a vector field, because if you remember, if we have a scalar function and we take the gradient of it, we get the vector that points in the direction that the scalar function is changing the fastest. So it actually gives us an equation of vectors. This is something that's actually very useful, and we'll talk about more, but it comes from electricity and magnetism, that an electric field equals negative of, the negative is there just for preference to positive charges, but it's the gradient of voltage, and that's actually where voltage comes from, kind of worked backwards to get to it. Rather than starting with voltage, you start with this force that's here, take force and you get electric field, and then the electric field, we figure out, well, what scalar field would that be the divergence, or not the divergence of, the gradient of. All right. And so then we've got here another one. This is just fluid flow inside a pipe, where it's going more slowly towards the edges of the pipe and faster in the middle. And again, another vector field right there. Here we have one, the radial field. This is a field pointing outward in every direction. This is actually something we'll talk about later that has to do with divergence. Notice that we are drawing this with the tails at the point that we're looking at. So it's not here. So if I'm looking at this vector right here, it's actually the associated vector for the base right there. So at the base here, that's where that's represented as pointing from, not out here at the tip, but back at the base. So just be, cautious of that. Here we have a field that has something called curl as it's going and would ultimately be a flowing around like this. We'd have some sort of swirling going on there. And again, we'll talk more about that, later. Here you can see a nice vector field of ocean currents or wind speeds, actually, it says. I thought it was ocean currents because it's only over the oceans and not the lands. But if you zoom in, excuse me, you can see that in the slower areas, you have these vectors that are shorter and pointed in a direction. And then in these higher wind areas, you can see that we have longer vectors pointed off in directions like that. And so this would be a vector. You'd give an XY coordinate and it would take you to somewhere like right here. And then you'd have that associated vector right there with it that had a magnitude and direction. All right. Here, talking about the gradient field again, if you take the gradient of a scalar function or scalar field, we end up with a vector function there because it gives you a vector. If you don't remember, del in Cartesian coordinates was partial x in the I direction plus partial y in the j direction plus partial z in the k direction. Just like that. And so we're dot it or just multiply it onto that scalar field and we get that. Here, an example for you, it says, suppose that the temperature T at each point in XYZ in a region of space is given by T equals 100 minus X squared minus Y squared minus Z squared, and that F of XYZ is defined to be the gradient of T. So find the vector field F. And so what we're saying is we want to find F, and F is the gradient of that. So we're looking into that. So essentially we're going to take the gradient of T, which means we're going to take the partial derivative of T with respect to X. That's our I component. Partial derivative with respect to Y. That's our J component. Partial derivative with respect to K. That's our with respect to Z, and that's our K component. And then that's it right there. The 100, of course, is a 0 when you take the derivative of it with anything. When you do the derivative with respect to X, that's 0 and that's 0, and you're just left with the negative 2X in the I direction. And then, of course, that's 0, and that's 0 when you do the with respect to Y. And then this becomes negative 2Y. And then everything else is 0, and that becomes negative 2Z when you do the derivative, partial derivative with respect to Z, because you treat everything else as constants. All right, so pretty simple there. Next, we have a definition here. Let F be a vector field with continuous components defined along a smooth curve, C parameterized. So the curve is parameterized, not our function, by R of T, where T ranges from A to B. Then the line integral of F along C is F dotted with T, where T is the unit tangent vector. And it's essentially what we're going to do for that one is to find a tangent vector, you find the velocity by taking the derivative of R. And then, of course, after you find that, you just divide it by its own magnitude. And so F dot T is F dot dr ds. And then that becomes F dot dr. And I really like this over here. And then we can actually put in the parameterization into the function and do F dot dr dt by dt, and that's back to us just being this F dot dr. You add the dt over dt in there, and so you get dr dt, and that's your velocity vector right there, essentially. All right, and so we come over here, and we can see this right here where we can do this. So to evaluate the line integral of F equals mi nj pk, where those are our nice little smooth curve along the parameterized curve. G of T in the I direction, H of T in the J direction, and K of T in the K direction. Take these steps. First, you're going to express F in terms of the parameter T by doing substitution, and you're going to substitute like this, where whatever is here in the I component, that's X, this is Y, and whatever's with the K component is Z, and you're going to substitute those in, and then you're going to find your velocity vector, dr dt, and you're going to then plug them in and integrate with this one that I have the blue box around, and just go ahead and integrate just like that. You can see down here where it says evaluate this F dot dr, and it's the same sort of thing. We're going to take this right here where we're going to say T squared is X. So this would come right here and go in right there, and square root of T would go right there for Z. And of course, then T would go right over here for negative Y squared. So you'd end up with what, square root of ti plus, you know, xy, what was xt squared times t again in the j direction, and so on and so forth. So you just make those substitutions and go through and do it. And I guess the very last one is just minus y squared, so minus t squared in the k direction, so like that. And just go through and make those substitutions, and of course do dr dt, and then go through and do it. So here you can see that I'm doing that right there. I've made those substitutions there right here down to this line. That gives us what our function is in terms of t. I'm finding dr dt right here, getting that. And then of course our boundary for t was 0 to 1 in our parameterization. So 0 to 1. So that's what I'm going to integrate over right there, 0 to 1. And so it's your integral of that function once we get it as a function of time times that dr dt, or dotted with that dr dt, and then integrate from 0 to 1. So here I am, I've got, here's f, here's dr dt, you dot them together into this scalar function of time, and then just go through, and I didn't finish it off because it's not a super hard integral, but you can finish off that integral and do it from 0 to 1. And then that's your line integral along there. We're summing up along that path. Okay. Here's another one. Evaluate the line integral here. And what you should do, here's your parameterization, is go ahead and pause it here. It's a little different than on the last one, but see if you can pause it here and try this one and figure it out as t goes from 0 to 2 pi. So give you a second here. If you need to pause it. And if you're still here, then here's the solution. You can see here that x is cosine of t, y is sine of t, and z is t, and that's taken straight from the parameterization, x, y, and z. And then I can figure out what dx, dy, and dz are by taking the derivatives of those. So dx is going to be negative sine t dt, dy is going to be the cosine of t dt, and dz is just going to be dt. So I'm just taking the derivatives and doing down like that. Now substituting these in, I put in so for this first one, it's negative y times dx. So I put in negative sine for negative y, that's that right there. And then dx is negative sine t dt, and that's that right there. So I just went through and did the substitutions here then for this one, and it gives you everything in that row. At that point, it's just a matter of doing your integrals with respect to time. And you can see here, I've gone through and done just regular old integration. And then again, from 0 to 2 pi, you plug that all in. Everything zeroes out except a pi. That's what you're left with, okay? So hopefully you were able to come up with that. Next, work done by a force is essentially just going through and summing up all the vectors that point in the direction of a line. You see, in physics, whenever you pull on something, like say we have this box down here at the bottom, if I pull out on this angle with this force here, F, the part that's horizontal and parallel to the direction of movement, to the displacement here, this delta S, is the only part that's actually contributing to the work. Any force that's perpendicular, that's not lifting that box up into the air, is actually just essentially getting wasted. It's going to essentially just create heat, but it's not going to do any work on the box. So that part just cancels out. So that's why ultimately you're taking force and you're dotting it with the direction you're going, with a tangent vector, a vector that is tangent to your curve. So that's the direction it's moving. And when you do that, you're taking just the component of that force along the path, and therefore you're adding up all the forces that worked along that path, and you add them up all the way along. So you're going to do like one, here a little bit of work, here a little bit of work, here a little bit of work, and just do work the whole way in all these little segments. And of course, we're going to take it down to the limit where we're going to an infinite number of these, where we're taking that limit as our steps go to 0, or not our steps, our step length goes to 0. And that's essentially it. You can do the same sort of thing to figure out what work is, and work is a scalar, not a vector, for it right there. So here you can see, just again, talking about taking the step and taking the component of the force that is parallel to the direction of motion at that point, because any perpendicular component here isn't going to be contributing to the work done on that particle or whatever is being moved. Here you can see the same sort of thing. Pause it and look at that if you want to, but again, you're taking the component of the force that's along that tangent vector. Here you can see a table showing different versions of how work is written out. The major definition up there, the compact differential form, all kinds of different things in there. I kind of disagree with that definition. I would say I'd define it as work is change in kinetic energy, but that's okay. This is, you don't have to know that. But anyway, I'll just erase that, not cross it out because it's not wrong. Okay, so there's just some different versions of the same thing, and you should be able to step through each of those and kind of figure it out like I did a few pages back where I multiplied by dt over dt, and you get that. There it is broken up in component forms, and then just the abbreviated component forms, and then of course, if you cancel out, but the dt's back out. Here's another example. Hopefully it's not too messy and you can kind of read that there. If not, just take a look in the actual notes online there. And it says, find the work done by the force field F equals y minus x squared in the I direction, z minus y squared in the j direction, and x minus z squared in the k direction along the curve r of t equals t in the I direction, t squared in the j direction, and t cubed in the k direction. And t goes from 0 to 1. And we're going from the point 0, 0, 0 to 1, 1, 1. So you can see I color coded what x, y, and z would all be. You substitute them into F. You take your velocity here, your dr dt, and then you dot them together and you calculate. Oh, oops, what happened? Oops, you dot them together, and I meant to hit undo and I clicked on the other document. You dot them together and you go ahead and take that line integral along that path. Okay, and so here you can see it being done. This is where it's actually done totally out. And it says, find the work done by that whole function and from 0 to 1 along that curve. And you get down there, you do that, you make your substitutions, make it a function of t, take your derivative of your path, put it all together, do the dot product, and then after you do that dot product, you integrate over that dot product from 0 to 1 what your range of t is, and this gives you just that 29 over 60. So if you need to pause and look through that math slowly, go for it. Here's another example. Find the work done by the force field F equals x in the I direction, y in the j direction, z in the k direction, and moving along the curve C parameterized by r of t equals cosine of pi I in the I direction plus t squared in the j direction plus sine of pi t in the k direction. And again, this will be x, this will be y, this will be z, oops, I got to get that t in there. This will be z, this will be z. I guess I didn't get the t in there on this one either. All right, it'll be cosine of pi t. There should be parentheses around these, just don't be confused. That it's pi, it's the sine of pi times t, not the sine of pi and then times t. So anyway, you can see here, I'm making the substitutions in. I've made the substitutions in, and then I'm coming down here and doing the derivative of each one. So the derivative and getting each one of these components here by doing those derivatives. Here you can do the dot product. You're left with nothing but 2t cubed after you do that dot product, because these two parts will cancel out. And then you're just doing the integral from 0 to 1 of 2t cubed dt, which if you do should ultimately end up being 1/2 for you. All right, so you should get that answer right there. Nothing too difficult for that integral. Here we're talking about flow of integrals and then circulation. So if we're looking at r of t as a smooth curve in the domain of a continuous velocity field F, the flow along the curve from t equals a to t equals b is our regular old here, is our line integral. So the integral in this case is called the flow integral if we're talking about this moving fluid. If the curve is a closed loop, the flow is called the circulation around the curve. So essentially same thing we've been doing, but we're taking the components of the fluid that are in the direction that the path is going through and adding them all up, right? We're taking those components. So it's still similar to what work is doing. So, how much water is moving along that path or along that curve or something like that. Here's an example. A fluid's velocity field is F equals xi, zj, and yk. Find the flow along the helix r of t equals cosine of t in the I direction, sine of t in the j direction, plus t in the k direction from t going from 0 to pi over 2. So starting off, I did dr dt first. You can see I just did the derivative straight there of it. So dr dt, just that derivative right there. And then I plugged in all of these parts. So I plugged this in for x, this in for y, this in for z, right up here. So this went there, this went over there, and this one went right there. And I plugged them in and I got this right here. You then do the dot product of them together and do the integral just as we've been doing. I stopped at this point. You can complete that integral if you want, but I didn't go ahead and finish it. Just as long as you know how to do it, continue on, finish that integral up right there. But ultimately, this is the integral you have to evaluate. Shouldn't be too tough. All right, next, circulation around a closed loop here. So we're going around this blue circle here. Again, the exact method is, again, the same. So dr dt first, right there, take the derivative, take your function and substitute in. So I'm putting this in for x and over here for x, and I'm putting this in for y right there, and that's giving me this function right there as a function of t. I then dot product my dr dt with that, so I'm dot producting those two together, gives me this. The sine squared plus the cosine squared part is just going to become 1, and so you end up with negative sine of t times cosine of t plus 1, and we're integrating from 0 to 2 pi. Again, you can go through and do that integral, and you should end up getting 2 pi. And that's the amount of fluid that's flowing around this thing, around our loop as we add it all up around, okay, the circulation there. All right, here, flux across a simple plane curve. So this one's going to be a little different. If C is a smooth closed curve in the domain of a continuous vector field F, M is a function of x, y in the I direction, n is a function of y, x and y in the j direction in the plane. And if n is the outward pointing, notice that, outward pointing unit normal vector C, then the flux across C is defined as that flux there, the integral of f dot n. So instead of dotting it with the tangent, where if this was our curve, we were dotting with the tangent vector t, the unit tangent, right? So we have some force here, and we're dotting with the unit tangent. If this is f, what we're doing now, in fact, I could just copy this picture real quick. Copy, paste that here, is we're not using the unit tangent. Now, what we're going to have is the unit normal at that point, in normal. And that's what we're actually going to be that's what we're going to be dotting the force against. And so this is not going to tell us how much of the fluid, like in this one, is actually flowing along the curve, right? What this is going to tell us then is what's flowing, what parts of it are flowing through the curve. We're taking that component that's perpendicular to the curve rather than the component that's parallel or tangent to the curve at that point. And so it's going to tell us about it flowing through it, and that's called flux, how much of it's going through that surface. So here you have some examples. All right, we want to distinguish curves that are simple or closed. So simple curves are not going to cross over themselves, and then closed ones, it's going to make that closed loop. So you can see the different examples there. Here, you can see the flux we're looking at is the integral of the normal component of F, and the circulation is the tangential component, T. So this is what we're looking at. So N is going to be T cross K. So you can see that. That's going to be T cross K. That's this pointed out this way. And then, of course, the tangent is tangent to it. All right, and you can see that here. And then depending on which direction you want to go, T cross K or K cross T, it can kind of change the direction of which direction we're going around that. But you want the outward flows, the outward flowing, you want the outward facing unit normal, not inward. All right, so just be careful of that. If you want, depending on whether or not you're doing clockwise or counterclockwise. whether you do T cross K or K cross T. All right, 1 second here. All right, sorry about that. So anyway, here you can see calculating the flux across a smooth closed plane. We'll indicate this here with this little circle around it telling us it's closed, and then you can see there's like a little arrow telling us that we're going in the counterclockwise direction there. So you can see that pointed in the counterclockwise direction, but we're going around a closed loop there, and that's what we're trying to indicate there, counterclockwise. Here's an example. It says find the flux of F. So that X minus Y is M. That other X that's there with J is is N. Across the circle, X squared plus Y squared equals 1. So here you can see we're just going to go through with our parameterization. R of T is cosine of T plus sine of T. That takes us around a circle. So from 0 to 2 pi. That's the path we're going around, and it traces the circle counterclockwise exactly once. And therefore, from that parameterization, we can get what M is. We have what M is and what N is from the function F. We can get what dy is and dx by doing the derivatives of those components. And then, and we also substitute it in, right? We substitute this in for x and this in for y here. And then we're doing the derivatives. Oops. That one's going wrong. We're doing these derivatives down here and the derivative up here to do that. Okay. And then after that, it just becomes a matter of doing this flux equation. So m dy minus n dx, and you go through and actually just, plug these things all in and take that integral, and it actually ends up being something pretty simple, and you just get pi right down there at the bottom. So if you need to pause and take a look at that and see if you can get that kind of an answer. Okay. After that, it's just some different paths you could take to get from 0, 0, 0 to 1, 1, 1. Certain things will be path dependent, where the path you take is going to change what your final result is. It's not just the beginning and end, but we will look at some where all that matters is the beginning and end. And that's actually in the next section, which is right there. So here, path is going to matter. In the next section, we'll look at certain types of vector fields where the path won't matter. All right, so anyway, that's it for now. Thanks a lot.